Hello my scholars, you are welcome to my school YouTube channel and my name is Frank. In today's video we are going to be discussing about simple harmonic motion. So relax, do not go anywhere and we'll be right back. Welcome back to my school YouTube channel. In today's video, like I said earlier on, we are going to be discussing about simple harmonic motion. So before we begin with this lesson, let's quickly run through the objective for today's lesson. So at the end of this lesson, the student should be able to 1. Define simple harmonic motion, 2. Show the relationship between I, linear and angular speed, II, linear and angular acceleration, 3. Show the relationship between period and frequency, 4. Calculate the energy in the system. 5. Explain forced vibration and resonance. So let's move to the next slide to begin with our lesson. So I will start by saying that simple harmonic motion is a special type of periodic motion. Okay, and in periodic motion, the part of the moving body is repeated at successive equal interval of time. An example of such motion is the motion of a body in a circular path with uniform speed, the oscillation of a clock pendulum, the vibration of a violin or guitar string, the vibration of the balance wheel of a watch, and the rotation of the earth about its axis. Okay, such vibrations play very important role in many physical phenomena, especially in light, mechanism, sound and electricity. So we define simple harmonic motion as the motion of a body whose acceleration is proportional to the distance from a fixed point and is always directed towards that point. So a particle undergoing simple harmonic motion will move to and fro in a straight line under the influence of a force. This influential force is called a restoring force, and it causes the body to go to and fro past the equilibrium position. Examples of simple harmonic motions are the prongs of a turning fork, mass hanging from a spiral spring, the swinging of a pendulum bob, loaded test tube floating and oscillating vertically in a liquid. So let's move to the next slide. So on this slide here, we are going to be discussing speed and acceleration of simple harmonic motion. And using this diagram, we are going to show that there's a relationship between simple harmonic motion and circular motion. And also from this diagram, we also show the relationship between linear and angular acceleration. And lastly, we'll also show that there's a relationship between linear acceleration and angular acceleration. Okay, so let's begin by showing you that there's a relationship between circular motion and SHM, which is simple harmonic motion. So we are going to be considering this diagram that is on the screen. Okay, so this is a particle P. Okay, and this line is called the projection of the point P. Okay, along the diameter. Okay, along the diameter of the circle YZ. Right. So and the point is labeled Q. Okay, so as this point P moves around the circle, the point Q moves to and fro along the diameter of the circle. Okay, momentarily at rest at Y and Z. Okay, as the point Q approaches the middle of the circle C, or the equilibrium position C, the velocity increases. So we can say that the point Q is performing simple harmonic motion, okay, as the point P moves around the circle with uniform speed. Okay, so let's move on. So from now, this figure is labeled figure A. So from figure A, the particle P moves around the circle once. It sweeps through an angle of theta, okay, which is this theta, and theta is equals to 360 degrees or 2 pi radian in the time t. So the period of the motion. The rate of change of the angle theta with time t is what is known as angular velocity. So basically, I'm just trying to define angular velocity, which is the rate of change of the angle theta, okay, with the time t. Okay, so mathematically, angular velocity is equals to angle turned through by the body, which is the theta, all over time taken. So that angular velocity omega, this symbol here is not W, but it's called omega. So omega, which is angular velocity, is equals to the angle turned through, okay, by the body all over the time taken. So we can make the angle the subject of formula so that we'll cross multiply, so that the angle theta becomes omega t. Okay, and this omega t is similar to the relation distance equals to uniform velocity times time. Okay, so what I'm saying in essence is that this formula theta is equals to omega t is similar to linear motion. Okay, where distance is equals to uniform velocity times time. Okay, and remember that in physics we represent distance with x, so that s is equals to vt. Okay, where s stands for distance, v is the uniform velocity, while t is the time. So that if we make v the subject of formula, v becomes x over t. Okay, so let's move to the next line. Now, what you are trying to do here is just to show the relationship, okay, between linear velocity and angular velocity. Okay, so let's move on. So as the angle theta in figure A is changing with time, so is the arc, okay, length x is equals to zp is also changing with time. And by definition, theta in radian is equals to s over r. Okay, of course, all these are shown in the diagram in the previous slide. Okay, so that theta in radian is equals to x over r. Hence, we can say that s is equals to r times theta. Now remember that r here stands for the radius of the circle. Okay, and we'll call this equation 1.1. Okay, and here a is equals to r. Okay, and r is the radius of the circle. So the angular velocity omega is given by theta over time is equals to, now in place of theta we are replacing it with x over r. Okay, because here we said theta in radian is equals to s over r. So we are replacing this theta with s over r. Okay, so theta now being replaced with s over r divided by t. So that, but remember that s over r over t is still the same thing as say x over r divided by t. Okay, of course, we keep the first fraction, which is s over r, then we flip the second fraction, which is t over 1. So that in that case, we'll be having x over r, okay, divided times 1 over t, right? So, but remember that this as well can be written as x over t times 1 over r. Okay, so the arrow and the t just changed position. But remember that x over t is equals to our velocity. Okay, but s over t is equals to v, right, which is our linear velocity. Okay, so that our omega velocity now is equals to v. Okay, because we've replaced the s over t with v. So that our omega velocity is equals to v times 1 over r. Or if we decide, of course, this is also the same thing as saying omega is equals to v over r, right? Because this v is also over 1, so that v will times 1 to give us v, and 1 will times r to give us r. So that at the end of the day, we'll be having v over r, right? So we can decide to make v, which stands for the linear velocity, the subject of formula, by simply cross multiplying. Okay, so that v is now equals to omega r. But remember that we said r2 is also equals to a, right? So that v is also equals to omega a, and we call this equation 1.2. So this is actually the relationship between linear velocity of a particle and the angular velocity, which is v is equals to omega r, or v is equals to omega a. Okay, but the a and the arrow are the same. They all represent the radius of the circle. Okay, so we can now say that hence the linear speed equals the product of the angular speed and the radius or amplitude of motion. So let's move to the next slide to continue with our lesson. So the linear velocity v at any point q whose distance from C, the central, is s, is given by v is equals to omega, okay, which is v is equals to angular velocity, then root a squared minus s squared, and we call this equation 1.3. Okay, so the maximum velocity Vm corresponds to the velocity at s is equals to 0. So when the distance between the center, okay, and the point q is equals to 0, which is x, as shown in this diagram. Okay, when the distance between C and Q here, which is equals to S, is equals to 0, then we will have maximum velocity, so that V mass, okay, which is velocity, maximum velocity is equals to omega A. But remember that A stands for the amplitude, okay, of the motion or radius of the circle. Okay, while the minimum velocity occurs at the extreme position of motion. So these are the extreme position of motion of the point Q. Okay, so the minimum velocity occurs at this point. Okay, remember that earlier on we even said that as the point Q approaches the center of the motion, okay, or the equilibrium position, the velocity increases. So maximum velocity occurs when x is equals to 0, meaning that the distance between point C and Q is equals to 0. Okay, the minimum velocity occurs at the extreme end of the motion, okay, extreme position of the motion. That is when x, okay, is equals to A, which is when s is equals to the radius of the circle. Also from figure A, we can obtain an expression relating linear acceleration and angular velocity using differential calculus. And one thing you must know that calculus is the language of physics. Okay, most of the formulas in physics can be obtained by differentiation and integration. So that is what we are going to be using here, differentiation in particular. So from figure A, s is equals to A cos theta. So this is it. Now we are looking for x and we know A, and we are given the angle, okay, between the lines CQ and between the line CQ and CP, right? And the distance CP is equals to A and the distance CQ is equals to S. So applying trigonometry, okay, we are going to be having that S is equals to A cos theta, okay? But remember that from our previous derivation, we said theta is equals to omega t. So anywhere we see theta, we replace it with omega t. So this is exactly what is happening here. So that x is now equals to A cos omega t, okay, where s is equals to displacement at time t of the particle from the center of motion. Okay, so let's move to the next slide to continue with our derivation. Okay, and omega here is the angular speed and A is the amplitude of motion. So differentiating, of course, we are differentiating s with respect to t. So we are differentiating A cos omega t with respect to t. Okay, and if we do the differentiation, we will be having minus omega A sine Wt. Of course, when we differentiate cos, it's going to give us minus sine. So that's why we have minus here. Okay, but remember that the s dt, of course, what we just differentiated is simply displacement. Okay, and the differentiation of displacement will give us velocity. Okay, so by differentiating the displacement x, we actually have velocity. Of course, and in order for us to have acceleration, we have to differentiate the velocity to obtain the acceleration. But remember that the s dt is equals to rate of change of displacement with time, and that is equivalent to linear velocity. So if we differentiate linear velocity again, we'll be having that. Okay, so therefore the s dt is equals to linear velocity, which is equals to minus omega A sine Wt. So to obtain the acceleration, like I said earlier on, we differentiate v, okay, with respect to t. Hence, A is equals to dv dt. Of course, if we differentiate this again, we'll be having minus, because when you differentiate sine, you are going to be having cos. Okay, so our minus sign still remains. So that omega, we multiply omega to give us omega square, our A still remains. Okay, that will give us cos omega t. Okay, but remember that A cos omega t is equals to S. So in place of A cos omega t, we replace it with S. Okay, so that the relationship between linear acceleration and angular velocity is equals to minus omega square s. Okay, and we call this equation 1.4. So we can say that the linear acceleration A equals the product of the square of the angular speed and the displacement s of the particle from the center of motion. So this equation 1.4 shows the relationship between linear acceleration A and angular speed or angular velocity. Of course, in physics, the word speed and velocity are used interchangeably. Okay, so let's move to the next slide to continue with our lesson. Now, one of the essential features of simple harmonic motion is that the acceleration, okay, and the restoring force are always in opposite direction to the displacement of the body. And also, the acceleration and force are always proportional to the displacement of the body from the equilibrium position. Okay, so next we are going to be seeing the relationship between angular acceleration and linear acceleration. Now remember that angular acceleration, alpha, okay, so this symbol is alpha, right, is defined as the rate of change of angular velocity with time, right? Now remember that in physics we usually represent angular speed or angular velocity with omega, which is this symbol that look like W, okay, but it's not W, right? Now omega t here represents the final angular velocity, while omega o here represents the initial angular velocity. So and we are talking about change in angular velocity with time, so that angular acceleration becomes omega t, okay, which is the final angular velocity minus initial angular velocity all over time. But remember that angular velocity is equal to v over r. Okay, remember that angular velocity is equal to v over r. So we are going to be replacing omega with v over r, or we are going to be substituting omega is equal to v over r into this equation. Okay, so anywhere we see omega t, omega r, of course these two are the same, so we can actually bring it out. Okay, we can actually factor it out, so that our alpha, which is our angular acceleration, is now equals to 1 over r, okay, times vt. Okay, of course our vt here is our final velocity minus initial velocity all over time, so that at the end of the day our angular acceleration is equals to our linear acceleration all over r, and r here stands for the radius of the circle or amplitude, okay, where a is equals to linear acceleration, so that the relationship between linear acceleration and angular acceleration, okay, is equals to a is equals to alpha times radius. So we can say that linear acceleration is equals to the product of angular acceleration and the radius of the circle. Okay, so let's move to the next now, and we call this equation 1.5. Okay, so let's move to the next slide. So on the next slide here, we are going to be defining some terms, okay, that are often associated with simple harmonic motion, okay, which are period, frequency, and amplitude. So we are going to be looking at what these words mean. Okay, for anybody performing simple harmonic motion, we can define the following term. So what do we mean by amplitude of a simple harmonic motion? So amplitude of a simple harmonic motion is the maximum displacement of the body from the equilibrium position, and it is denoted by letter A, okay, capital letter A. So let's define the second term, period, and period is denoted by letter T, capital letter T. And period is defined as the total time taken by the vibrating body to make one revolution or circle about a reference point. Okay, so mathematically, period is equals to T over N, right? Where T stands for time and N stands for the number of revolution or number of circle, and we call this equation 1.6. Okay, and remember that period is measured in seconds. Okay, while the third term, frequency of a simple harmonic motion, is defined as the number of complete revolutions per second made by a vibrating body, or you can say it is the number of complete circles, or it's the number of circles, okay, it's the number of circles per second made by a vibrating body. So mathematically, frequency is equals to N all over T, where N stands for the number of revolution or number of circles all over time. From here, okay, you can see that the relationship between frequency and period is that frequency is equals to 1 over T, meaning that frequency is the inverse of period, okay, and we call this equation 1.7. So the SI unit of frequency is called hertz, right? Is the hertz, and 1 hertz is equals to 1 cycle per second. Okay, 1 hertz is equals to 1 cycle per second. So let's move to the next slide. So we are still continuing with our derivation. Okay, so apart from those two formulas that I gave in the previous slide, we still have other formulas that we can use to calculate period and frequency of a simple harmonic motion. Okay, so I just want to show how we got the second formula. So remember that omega is equals to theta all over t, right? But here we are saying that t is equals to period. Okay, t, which is the time, is equals to period, the big letter t, and the period of simple harmonic motion, or the time for one complete cycle. But remember that theta is equals to 360 or 2 pi radian. So we can say that omega is equals to 2 pi over t. Why? Because theta is equals to 2 pi radian. Okay, so that in place of theta, we replace it with 2 pi. So that our omega is equals to 2 pi all over t. Here, we say the t time is equals to period. Okay, so that if we make t the subject of formula, we'll be having that t, which is the period of the simple harmonic motion, is equals to 2 pi all over omega. Okay, and we call this equation 1.8. Now, similarly, we know that the relationship between frequency and period is equals to 1 over f, right? So we just bring this here. Since our t is equals to 2 pi all over omega, so anywhere we see t, we replace it with 2 pi all over omega. So that we'll be having 1 over 2 pi all over omega, right? So since we're having two steps of fraction, okay, the last term in the fraction will move to the top, so that our frequency is now equals to omega all over 2 pi. So these are the other formulas that we can use to calculate period and frequency of a simple harmonic motion. So from here, we can as well get our omega to another formula for calculating omega to be equals to, omega is equals to 2 pi f, right? Where f here stands for frequency, right? Since our frequency is equals to omega over 2 pi, then we can make omega the subject of formula by simply cross multiplying. So if we cross multiply, we're having that omega is equals to 2 pi f, right? And we call this equation 1.9. So below are some examples for us to apply these formulas. Okay, so let's begin with example 1. A particle makes 240 revolution per minute on a circle of 2 meter radius. Find its period, angular velocity, linear velocity, and its acceleration. Let me go through the question again. A particle makes 240 revolution per minute. That's what RPM means here. Revolution per minute on a circle of 2 meter radius. Find its period, comma, angular velocity, comma, linear velocity, and its acceleration. So let's move over to the board to solve this question. So as usual, first thing first is to write out the parameters that are given to us in the question. So our frequency, okay, is 240 RPM, right? But remember that our frequency cannot be in meters. So in that case, we have to convert this to seconds. So to convert this to seconds, so that at the end of the day, we'll be having revolution per second, not revolution per minute, because this simply defines, this term here, RPM, simply defines frequency. Okay, so in that case, we simply divide 240 by 60, because 1 minute is equals to 60 seconds, right? So we simply divide 240 by 60. So we divide 240 by 60, and this will be equals to 4, right? Because 0 will cancel 0, and 6 into 24 is 4. So this becomes 4 rev per seconds, not minutes. So this is our frequency. Now we are told that radius is equals to 2 meters. These are the parameters that are given to us in the question. So the first thing we are asked to find there is its period, right? But remember that the relationship between period and frequency is that of inverse, right? We know that frequency is equals to 1 over period, right? So that period is also 1 over frequency. But from the question, we are given frequency, okay, to be equals to, from our calculation, we got frequency to be equals to 4 revolutions per second. So here we just substitute. So that we'll be having 1 over 4. And 1 divided by 4 is equals to 0.25. And remember, period is given in seconds, measured in seconds. So our period is equals to 0.25 seconds. Okay, so the second thing that we are asked to find is angular velocity. Right, we are asked to solve for angular velocity. Okay, so let's call this 1 and let's call that one I, so that will be proper. Angular velocity omega is related to frequency by the formula 2 pi f. Okay, so we already know our frequency to be equals to 4 revolutions per second. So we just substitute it here. So this becomes 2 times pi times 4, and that will be equals to 8 pi, right? So we are leaving our answer in terms of pi. Okay, so that will be equals to 8 pi rev per second. Okay, so let's solve the third question. So the third question, we are asked to calculate linear velocity, right? We are asked to calculate linear velocity. And remember that there's a relationship between angular velocity and linear velocity, and that is given as v is equals to omega r, right? Remember that from the question we are told that the radius of the circle is 2 meters, right? So we just substitute, since we already calculated for omega velocity in the previous question, so that v is equals to, our omega velocity is 8 pi radian per second, so we substitute it here. So that becomes 8 pi times 2. So in that case, this will give us 16 pi meter per second. Okay, because we are dealing with linear velocity here. Okay, so now let's move to the fourth question, which we are asked to calculate, and we are asked to show its acceleration. The acceleration that they are talking about there is actually about linear acceleration, right? And remember that there's a relationship between linear acceleration and angular velocity, and that is given as a is equals to omega square r, right? It's given as a is equals to omega square r. Okay, so that a is equals to, of course, our omega is given as 8 pi radian per second. So that we'll be having 8 pi in bracket square, then times 2, right? So that if we take the square of 8, that will give us 64 pi square, right? Then times 2. So if we multiply this together, that will be equals to 8, and this will give us 12 pi square. And this is meter per second square. Okay, since we are dealing with linear acceleration, not angular acceleration. So the answer to the last question there, which is its acceleration, is equals to 128 pi square meter per second square. And the reason for this is because we actually calculated linear acceleration and not angular acceleration. Okay, so this is where we draw the curtain for the preview of today's video lesson, and I hope you enjoyed it. You can enjoy the complete video by clicking on the link in the description below. This will take you to my school website. There you have to subscribe to enjoy the complete video, and in the complete video we solve more problems where we apply these formulas, okay, that we have derived in solving more problems. We also talked about the energy of simple harmonic motion, where we also show the period of vibration of a loaded spring. Okay, we also talked about the types of oscillations, such as forced oscillation and resonance with example, and we also did more calculations so that you know how to apply these formulas when you are given problems. I believe you enjoyed this video. If yes, please do not forget to hit the like button, click on the subscribe button, and lastly, tap on the notification bell to get informed as soon as we release the next video.